So let me move everybody's faces to the side so I can actually see what I'm presenting. And hopefully you're seeing the right screen that says Monty's new capability, learning surface models. Yes?
Yes. Yep.
Yeah.
Okay, great.
And I guess
Um,
not just learning them, but dealing with distortions during inference
yes.
is a
Surface
big,
models in general, I guess.
yeah.
Not just learning, but there's also inference. Uh, okay, so learning surface models, what that is will become a little bit clearer as I get into it, but um, I put this Excalibur, or part of an Excalibur board from back in February, where Vivian was talking about different kinds of models we might have. Um, so this was in the context of behavioral models, which like, I won't really go into, but basically there were kind of four different kind of categories depending on the input to L6 and L4. So there can be movement in 3D space. I mean, the top left is what we already have. That we have an agent that moves in 3D space. We extract features like colors or surface normals or other morphological or non-morphological features to learn a 3D point cloud object model. What I'm going to be presenting is mostly on the bottom left here, where we added capabilities to extract movement, kind of extract corresponding 2D movement in 3D space. So Monty is still moving in 3D, like nothing about the environment has changed, but we're going to extract the 2D movement out of it. And also, there is one additional kind of feature extraction that we added, which is being able to detect dominant edge orientation in our image patch. So there were kind of two independent but related functions added. So that's what the
Can
text
you can
says.
you remind can you remind us, Hojae, what was the motivation for working on this?
That's the next slide, which is trying to recognize compositional objects. So I think so. So many obviously just for Benji, compositional objects. The simplest definition is object made up of other objects. I realize that's like using the same words, but basically, you have examples where TP's logo sticker is one object, this cube is another object, but together as a whole, this can be labeled as cube with TP logo, something like that. And so we have this kind of broad quarterly goal of trying to recognize compositional objects. So, I mean, this is a little bit behind the brainstorming. I know brainstorming we kind of figured out the compositional objects, but
Well, it's
um,
interesting. I just want to point out that compositional objects doesn't require 2D solving a 2D problem, right? An intersection
that
with
is true.
cars are 3D objects in a 3D environment, and that's a compositional structure. So
Yeah.
what you're really saying is we have two-dimensional objects such as the logo, and we're applying them to
Yes.
a three-dimensional object.
Yes.
Right. And and the logo is not represented uniquely, is it? Or is it? Or are you saying it is going to be represented differently? I mean, is it? Well, I'll let you keep going.
Okay. Yeah. If you want to break your question again, feel free to do so. But yeah. So it's not a strict true representation. It's not a strict requirement, but it's a useful representation for Monty to have to uh, recognize the kind
This
of
is this is a
yeah.
specific problem we had with two-dimensional structures like words wrapping on three-dimensional objects.
Yes.
Right. It's not compositional in general. It's just a specific corner case in some sense. Yeah.
Yes.
Yeah.
It was pretty general about distortions, like recognizing the logo on a t-shirt and um,
Right. But it's always it's
Or
again it's a
even
two-dimensional
recognizing the
object.
crumpled T-shirt itself. Like
yeah.
we haven't demonstrated that, but in principle,
Okay.
the same techniques could be applied to build a 2D
Well,
model
okay.
of
Well, so
the T-shirt.
that's why I asked what the motivations were because it's more than just compositional objects.
Oh yeah, definitely it's more the yeah. I'm just sorry. The lead up to this was like one framework for motivation was this because this is our current overarching goal. But this 2D model I think will be used beyond compositional optics as well.
Okay.
Hopefully.
Yeah, so
Well,
it's a general powerful new capability to recognize like logos on various surfaces to deal with distortions, not just logos, but anything. Um, but
Well,
we
I guess
decided to do it now because it was a prerequisite to deal with this compositional data set.
okay, but
And
I want to be clear. It's not just two-dimensional objects on it, right? You said it could be just a deformation in the t-shirt itself, right?
yeah, or it could be, so of the two kind of features that Hojae talked about on the previous slide that had to be implemented, one of them is specifically for kind of when you have this intersection of 2D objects on 3D objects. That was the kind of accounting for the movement in 2D space. But the other one of kind of detecting dominant edges, that's just detecting basically morphological features in
Yeah.
2D space. And that we didn't have before. So
That's what the
we
one we
didn't have a,
discussed that's the one we discussed
yeah.
with the t-shirt, right? And the cable and all those things. Is that right?
No, that I'm more talking about detecting like edges of a word, like or assume you have a photo of a face, detecting
Yeah.
the edges that correspond to the that outline of the face. So
Okay.
that in order to kind of recognize like a line drawing or something like that, you could use that, but we didn't, or let's say letters or words. Um, you could build
Right.
models based on
But
those
then again,
morphological features.
but those are again two-dimensional objects. If I have a line drawing of a face, it's a two-dimensional
Yeah,
object,
exactly.
right?
But so all of this is basically enabling capabilities in 2D space with 2D
Okay.
objects. And one instance where those appear is in composition with 3D objects,
Okay. Well, that
which
helps
is
me.
why we decided to work on it now.
Okay. No, it's good to work on. Just I want to
Yeah,
understand motivation.
right.
Yeah.
Okay.
Yeah, so again, one way to frame it is how can you recognize the TP logo stickers that are on different 3D objects? Again, one narrow case of it, but for example, with our current Monty, we can learn a 3D object model, maybe just on the logo area. So on the cube, you can kind of learn this Thousand Brains project. Area within a cube, and you can see that, oh, like with this learn model I can recognize it on a different surface like a disk, because both of them are flat. But then we would have trouble uh, some trouble like maybe generalizing to curved surface like a cylinder or mug, and I realize the mug isn't it's not overlapping completely, but that's not an issue with the model. It's just my skill in visualization is limited. It's supposed to be overlapping, but anyways. So again, with the main thing about the 2D model is 2D surface model is that now we can learn a 2D representation of the same TP logo, or whatever you want, in kind of in a consistent manner across different surfaces. So okay, so I know this is a little bit busy slide, but I'm going to start kind of from this bottom right area. So here I'm showing the Learn 2D model of the TP logo on disk. I know it looks a little bit ugly, but we still have the same kind of point cloud Learn model. It's just in 2D, and so everything is flat. And I put some red lines wherever we detected an edge. So for the TP logo, kind of looks like the outline of the um, is this neuron? I forget what this represents. The neuron and the logo, and the border, the sticker border itself. The sticker border is the white
No,
against
I'm
this
sorry,
yellow background.
Hojae, but when we say learn it on the disk, it's just the two-dimensional logo, right? It's nothing to do with the disk, right? It's just a flat logo,
Yeah, yeah, it's just a flat
right? So
logo. Yeah.
we've learned a two-dimensional logo, and the
Hmm.
challenge is to now not only do how we recognize it, infer it, but how do we make predictions about it when it's on a curved surface? Would that be the
Yes.
correct? Okay.
Yes.
So
Yeah.
all
We
right, so
also tested the reverse of you see the logo on a mug, you learn it on a mug, and then you can recognize it on a flat surface afterwards.
oh, that's pretty cool. Anyway,
Yeah.
my point is TB logo on this isn't really TBT logo on this. It's just the two-dimensional logo, right?
Yes.
And in fact, it's on a disk,
Same
doesn't
for the
matter.
cylinder. Yeah. Yeah. I mean,
Well, the
well,
cylinders,
I
no,
kind of
that's not true. The cylinder is curved, right? So when you're on
yes.
the cylinder, you're on the curved surface, which is the challenge,
Yes.
right?
Yes.
So I just want this, the language trips me up. So it's just like, oh, we have the TBD logo as it's in its native form, which is the two-dimensional structure. And now we're going to wrap it in 3D on the cylinder.
Yes. Yeah.
Okay.
But we can learn the TP logo from the cylinder. This is the learned TP logo that was attached to a cylinder, and we can still extract a 2D surface model out of it.
Okay.
Like,
That's great.
yeah. So yeah. So now, like, I know this like doesn't look perfect, and I know Nils and Vivi, you might have questions why it looks kind of weird, especially on either side. I have a good answer for this, but it gets kind of into the implementation details, so we'll come back to that at the end. But the point is that we can recognize kind of similar. The representation of the logo is, I guess, more independent of whatever the underlying surface that we learned it from. So basically, what this heat map shows is that we can learn the logo at different surfaces, just the logo itself, or from the disk, like this one, cylinder, like this one. I didn't put it in for a sphere or a mug. We can learn it, and we can recognize it in other surfaces with, decent accuracy, I would say. For example, at least on the 100% column, this means that we can learn the logo from any surface or any surface, and we'll be able to recognize just the logo itself, just the sticker part itself, with 100% accuracy. Yeah, that's it.
Yeah, it's maybe interesting that the sphere seems to be the most challenging to transfer from, which would be kind of consistent with our intuitions about what is kind of causing the most distortion.
Yes.
But it's, yeah, as you say,
It's also,
performance is still good.
I mean, you're treating the logo as an object, a non-compositional object, right? Well, in fact, the logo is a compositional object. It has
Yes.
multiple components, and it's words and words of letters and so on. So this would be like I'm recognizing this thing, even if I had no idea what words were and what letters were. Um,
Yes.
and so you can see why that's a harder problem. You and I would have no problems at all recognizing this logo immediately because we'd read it. We would know the words, and we know it as a compositional structure. So I just want to keep that in mind because I
Yeah.
think if we treated this as a compositional structure, you'd get 100% on all these things. At least you should. The fact that we're treating it just sort of this, so almost like bizarre random bit pattern, um, makes it harder for the system, but it does pretty well.
Yeah. And actually, that's kind of possible next thing I might be working on is we need to create more compositional data set because by the same issue of like, okay, but this logo itself is compositional and we're recognizing in a child object, but technically, yeah, as you said, it's made up of, words and letters.
Right.
Anyway, so that's
Well, this is your
yeah, main
results.
thrust of it.
You,
Yep.
you going to talk about how you did it?
Oh yeah.
Okay.
A little
Okay.
bit, yeah. But I mean, it's kind of more for the users to kind of understand the behavior of what was implemented. So okay, so I'm going to have a couple slides for each of the two components. So I'm going to talk about the detecting the dominant edge in a patch. So again, this is one of many sensor modules already. We could already extract a lot of features. This is just one additional thing that we added. So it answers the two questions. One, is there a dominant orientation near the center of a patch? And if yes, what is the angle or vector that represents this direction?
Yeah, it's maybe worth highlighting like it's not just kind of another feature in the sense that it's like it is the morphological feature in 2D space, where the
Okay,
surface
yeah.
normal and the curvatures are the morphological feature in 3D space. So
Right.
it's
Thank you.
it's the
That
most
makes
important
more
one.
sense. This is what you see in V1, right? You see edges,
Yes.
patches.
Yes. And yeah, so just to give you a sense of behavior, so if you have a simple black patch with a straight line, easy to detect. It can be a little bit low contrast, still very easy to detect. It can get blurry, it will still detect it. Maybe at this point we might, so computer vision people might say like, oh,
Are
this
you
is not an
saying
edge.
are you saying the feature detector you've implemented does this, or this is what we should be able to do?
This is what we implemented, does this.
Okay.
Yeah, so we made some like explicit algorithm or design choices so that we would allow for detection of edge even
Okay.
when we have a blurry line here. Yeah. I mean, I feel like we use the term edge detection, but I feel like that is like a misnomer because it's not. It's a lot more, I guess, complicated than that. um, and it might not, like, you might not think of this as an edge kind of canonically. Like you might only think of as sharp edges, but after discussing kind of what kind of behavior, what kind of things that we wanted to type, um, that's why I'm trying to say, trying to uh, detect dominant orientation, but it's just more of a mouthful to say than edge detection. Anyways, so our current implemented edge detector in TP Monty will recognize this as an edge despite being blurry. It can be slightly off center. This is kind of an extreme case, actually. It can be, so it doesn't need to be exactly in the center. If it can be off, but we'll still allow for it. But we'll still reject if it's too far off center. So you can see how things are getting a little bit complicated. There might be actually another kind of distracting edge, but in this case, we're going to say that the vertical one is the dominant one over the horizontal line. So we're going to say that we do detect an edge, and the angle is following the vertical line. Obviously, if the horizontal line gets thicker, then that's going to be the detected edge. And yeah, I mean, so we basically, the point is that we consider a lot of different cases to kind of think about what it is that we want the edge detector to behave. So in this case, we have two lines technically, but the vertical is the dominant one because it's closer to the center. And this one, actually, the yellow line is a mistake. There shouldn't be any edge detected. But there can be cases where we have kind of multiple dominant orientations. And one, we should be rejecting them, as in we'll just say there's nothing detected. There's no one single dominant edge. But since everything is kind of based on a threshold, if you do detect something, it is possible in very rare cases that you might get an angle that is not representative of either two because the edge detector assumes that there's only one dominant orientation. That's a
You're going to
caveat.
explain. You're going to explain how this works.
Um, Not any further than this.
I mean, the algorithm underneath the algorithm is because in real images it never looks like this. It's
Yeah,
really it's very all kinds of crap all over the place. And
right.
so I mean we kind of have a sense how the brain does this with the center surround receptive fields. And putting them through like a spatial pooler. So I mean if you require clean images like this, it's not going to work in the real world. And
Yeah.
so the question is, how did you implement it, and how would it handle these? The fuzzy cases are the ones where it's like not just fuzzy, but like you know, I've seen images. If you zoom in on an image of something that looks like it has a clean edge, when you
Hmm.
zoom in on it, you realize it's not clean at all. Your brain
Hmm.
makes it look. Your brain says it's clean, but in reality, it's not clean. So the real case we have to handle. We have to handle these, but we also have to handle one of the ones that are much more natural. And I'm just curious about knowing the algorithm that you implemented to do this. I don't know how it's going to handle those.
Um, yeah, I have some examples of, okay, so how what it looks like, and I guess probably should have put in a little bit more examples of patches that Monty sees. So these are parts of the Thousand Brains logo. It's just zoomed in. So this, I think, is a U and an S in the thousand. And yeah, I mean, we went through, I mean, simple to hard, or at least cases, because genuinely, like when you look at the real patches that Monty sees, it's a lot more complicated to,
What
even for
what
us, to
is
decide, oh, what is the dominant edge or
so
not.
this is the entire patch that's being fed in these lower
Uh,
images?
yeah, so each of these squares are one patch that Monty would see in a single step. So this is our straw world
Mhm.
patch.
And what does the blue arrow represent?
The blue, ignore the blue. The yellow is where the edge is. The blue is for the perpendicular of it. Yeah.
Okay, ignore the blue. So the yellow is representing the detected dominant orientation. Is that what you're
Yes,
saying?
yes, that is correct. So Again, it's a little bit.
So
So
I'm interesting, like on the ones on the right there, we're looking at the two on the very right,
mhm,
blur 1 versus 3 on the right,
this one, yeah,
blur 1 versus 3. I mean, it's interesting. Why I wouldn't even assume there's an orientation, dominant orientation to those. I mean, it's that if I imagine if I fed that, got information, I fed that into a bunch of center surround receptive field cells. I'm not sure that the cortex would pick out, say, there's an edge there. It would probably narrow its focus down to a smaller area and then say, oh, what is the dominant edge of the U or something like that. So
right.
it's just curious that I think it seems like this will give you a lot of issues if you're trying to detect the dominant edge of some of these images where it's not clear there is one.
Well, the
Yeah.
Is
idea
that
here is that if we're not zoomed in far, we want to blur the image, like the right version. And so in this case, if we have a patch that's not very zoomed in, so you have a lot of
oh
fine-grained detail, you blur it and then you detect the orientation of the word.
so blurring is part of the algorithm.
Yeah.
Yes, it's
Oh, I'm
Yeah, it can
sorry.
be.
I don't know if you're going to explain all this. I mean, what are you going to
it's a
explain?
little. I mean, I have a document that I have written out, but it is quite
Well, I'm
mathematically.
sorry, but I think
Yeah,
this is a research meeting. I think it's important to understand what you've done because if we're gonna live with this for a long time, we have to understand how it works. So I didn't know that you were
yeah.
blurring it to that, right? Um, so the idea that you blur it until you feel you get a dominant edge, how does that work?
It's so the first thing is that like we zoom it in to 30 so that we will have for the most part approximately one dominant orient edge within a
So you
patch.
so
But
you zoom
it's
in close, you zoom in close until you see an edge. Is that what you're saying?
No, it's not
No,
a
we
dynamic thing. It's the patch generally is quite zoomed in, so it only sees a very local area. Those things don't happen dynamically, like neither the zoom nor the blur. It's more saying
Oh,
if you have a small receptive field, like 30 times zoomed in, then maybe you don't need to blur as much. But if you have a larger receptive field, like only 10 or 20 times zoomed in, then you want to apply blur as well. And that's more like a config parameter you have to set in the beginning. Like you don't want to have a large, high resolution receptive field in general. It's kind of independent
hmm.
of the algorithm.
But this really depends on how far the object is, which
Right.
you might not know in detecting. Like if it's too far, then
Well,
you would need to
it's
blur.
it's not just distance; it's also just the magnify. I could have the logo could be printed very small. It could be printed large.
yeah,
Right.
Um,
Scale, yes.
But yeah,
yeah,
the general idea is that if it's a less zoom, it's going to blur so that it's looking for coarser edges in the world, but that tend to be larger, like you know a word or something like that. But yeah, you're
mhm.
right that obviously it'll depend on the exact size of the print and things like that. And so we'd imagine that we might learn multiple different models based on yeah how we had seen different things, and then we can also account for scale and variance with some of the other stuff we've talked about um, in terms of kind of movement. But but I mean, in some ways, the yeah, I guess as long as the positions of the edges kind of match up, it doesn't matter too much. Um, yeah, where exactly or what they exactly correspond to.
Mm.
If it's like the word, the
It's
bottom of the word or bottom of a letter.
it's interesting that it's just intuitive. I feel that this is dynamically managed in the brain. Like, I'm not sure if
Yeah,
it's
that is
attention
something
when,
we could explore. Kind of
right?
adding.
Because I think because otherwise it's going to be problematic. And then, yeah,
yeah. That's.
yeah.
I mean, there's definitely a underlying scale issue, right? Like that we're only using zoom equals 30 because the kind of the logo, the size of the logo, like the literal physical size that we see in the simulator, is kind of small. So we have to zoom in very far
Right,
to
right. You're
actually get
tuning it
one.
you've tuned it to the data set, which, the
Right.
logos will be in all different sizes.
Exactly.
Another thing is since we're not really treating this as a compositional object, We talked about this before, like words, often we recognize words when we're reading, we recognize them without attending to the letters, right? And this is why it's easy for us if I have two words that have the same length and they have the same beginning and letters and they have similar shapes overall, we can often confuse them, or we don't notice that they're mistyped, that there are typos in it. So the letters can be incorrect, but we still recognize the word.
Yeah.
And so that tells me that these sort of morphological models that we're talking about, these are pure morphological models. There's no children involved. That we don't really have all this detail. The models themselves, typically in our heads, would not include all the details in the middle. Imagine if these letters were written in a language I wasn't familiar with. So they're written in Arabic or something like that, or Chinese. I wouldn't be able to tell these one from the next. I could only judge by the general shape and maybe the outer edges or something like that. So we might also be asking too much of the system at this point in time. Like I'm thinking, like, would the brain actually try to take these two, the ones on the bottom right here? Would it actually um, form any representation of them? It would be very, it's like in the middle of the word. You know what I'm saying?
Well, the
Okay,
way
Yeah.
the way I was thinking of this is, yeah, in this case, we kind of have to tune the zoom factor and the blur to our data set because we only have one sensor module and one learning module. But in the brain, you'd have many receptive fields in many sizes and resolutions. And so, kind of like you said a lot of times before, Jeff, if you have a small letter A, you would recognize it in V1, and if it gets
right,
larger, you
right,
might recognize it higher
right,
up,
right,
like in places where they have a larger receptive field. So you just have different learning modules with different
right.
models. Some
Right.
of
That
them
is
learn like a low resolution
right,
version of the shape
right,
of the word, and others
right.
learn the individual letters.
I'm
Yeah, and
also
the idea
thinking
with
that
the one on the right is to learn kind of like you're saying, like the shape of the word. So because it sort of it cannot see almost like the edge within the U or the S or whatever, but it can see
right,
the shape of kind of the outline of thousand.
right,
And so
right.
that's what it's actually going to learn. But then we'd have another one which would learn, the actual individual letters, and
Well,
that
only
could
be another
form a
one would
compositional
be
object.
well, that other one would be a different region. It would be like V1, V2, V4 type of
Yeah.
thing.
Yeah.
Um, right. Okay. Yeah. Okay.
All right.
I think what we'll find is what I think. We'll find that when we start putting this in the real world, there's going to be a hell of a lot of tuning or modifications we're going to have to make to this. But it's a good start. So I think that's great.
Yeah. And yeah, so I'm giving you or like this user is, like the kind of behaviors, and then obviously that this is why I put like if you're using for whatever reason this particular data set, compositional data set version 1.1, you will see that I use a zoom 30 and a blur of some value. It's more to explain like why I set this, because like if you were to where somebody were to like fine tune this, where do we even start fine tuning? My recommendation is go to one of these two parameters to kind of make sure that you're kind of looking at one dominant orientation ish per patch. But obviously it's only for this data set, so
Well, I guess the
it's
trick is
yeah,
the thing is we don't want to fine tune it, right?
right,
That's not what we want to do. We want a system that's robust without tuning, and so we're just discussing the different components of that
yeah,
right now, right? So
Yeah,
clearly, one is to have different levels of resolution at different regions. Um,
yeah.
okay,
Also, if it's interesting, if if you even look at V1, for example. The patches in the retina in the fovea and the center receptor field, of course, are very small. But if you look at what the columns represent when you go further out on V1, they get very, very large. So V1 is not consistent, right?
yeah,
V1 covers the entire visual entire retina, but once you get out of the foveal section, the areas represented. And presumably those columns that are beyond the fovea are building the same models as we have inside, but they're doing a much lower resolution. So if I were looking at an object and we're invoking multiple columns, some of those columns, if the whole object is not contained within the foveal area, um, The ones in the foveal area will be high resolution, like you're doing with here, but the ones would be further out would be very, very blurry. It's just something I'm not. All I'm saying is that just we have to keep that in mind when we think about building practical systems. That
Yep.
even V1 is not low resolution everywhere. Or high resolution. It's only in the foveal area that's high resolution. Everywhere else it gets pretty crazily blurry.
Yeah. I'm sure we'll probably think about it like when we get to like dealing with multiple, like not just two sensor modules, but like hundreds that can actually kind of represent I instead of just this one LM, one SM cases. But I feel like a lot of the research still, at least in the implementation side, where a lot of the experiments are still on the one learning module, one sensor
Yeah,
module, even though we're
yeah.
kind of moving away from that, like with the compositional, like,
But
but it's still like a
we have to
handful.
think about it. It's worth, if you don't mind. This is a research meeting, so we're used to doing brainstorming. So I'm gonna
Yeah,
interrupt
go
you.
ahead. Yeah.
Um, the more I think about, I was just thinking about, okay, imagine V1, you got this a whole bunch of columns, a whole bunch of learning modules. The learning modules are all the same, but the amount of area of the retina or the camera they're looking at changes dramatically outside of the center. And so even when if I was thinking about in V1 and I'm reading a word, that word may span. It may go. I may be looking at I'm looking at the word genuinely right here on your page. It's in the second to last line.
Yeah, I can
And
hear.
right, and so I'm focusing on the G, and of course the rest of the word is there, but it's just totally hard. It's like it's no detail to it. And I think that's even, and of course I know it's there, and I zoom over there and I see it. My point is when I learn even V1, we'll be learning words where it's going to part of V1 is going to be saying, okay, this part's really blurry. I'm learning a model. I'm looking at a much larger area, and I say it's looking at a much larger area of the retina. Another part of V1 is looking at a much smaller area of the retina, and that whole system is trying to learn the word. It's not like just the foveal area is learning the word. And so the columns on the periphery are learning the words too, but they're going to be very so. Even V1 could. I just realized that even V1 could learn larger objects in some sense. And V1 would say like the the center part is trying to deal with the fact that you're looking at these fine details, but if I could learn the fuzzy recognition of the whole word in V1 as well, um, using the more peripheral columns.
Yeah, and as you're kind of scanning the sentences, that could predict what you're going to see next. So, like, I don't know, maybe
Right.
those columns might think they're going to read the word hard, or it could be harp, or I don't know, something like that.
Right,
And then,
right. Right. So,
um,
right. So the column, if I look at the G on genuinely, some columns are looking at a very blurry end of the DUINNLEY, and they're just sort of recognizing sort of a general shape, which might be consistent with not a similar combination of letters that are like INALY or something like that. Um, uh, all right, yeah, I'll stop there. I think we have to consider the possibility that even a single region like V1 is able to handle objects of different scales quite well. And in some cases, it's going to be relying on the more peripheral columns more. In other cases, it'll be relying on the more central columns more. Um, and that even a
Yeah.
single column like V1 could handle a great deal of variety. It never really occurred to me before. That's worth thinking further about.
Yeah. And this is could be my hubris, but I think the edge detection works pretty well in different like resolute like different zoom settings and the blur, or at least we're getting reasonable orientations. So I mean, but when we have V1 where we have different resolution, the kind of or blur, whatever. I mean, it's. I think at that point that's a question of how do we put this kind of together to recognize the word genuinely or hard, but at least the individual patches that are kind of looking at really zoomed in or far away, like we're catching a lot of cases. Maybe that's
Yeah,
my
and
that maybe
and
I
that's my
think
hubris.
it's a pretty general edge detection. So if we just have different sensor modules that get different zooms and resolutions, we would have different learning modules learn different different models of the words. So one might be learning the model of the G, another might be learning just the length of the word genuinely, and the rough outline of it. And then through associative voting, they can still inform each other and very quickly resolve which word it actually is.
yeah, and as mentioned earlier, like the parameters which affect how the edge detection works, there's no reason we couldn't change those dynamically if we wanted attention to to modify them. But we just don't have kind of the attention
I don't.
system working yet to do that.
Right. So
But yeah.
I was thinking about, well, you could dynamically change it, and I said that, but then I'm thinking of other mechanisms where it doesn't have to be dynamic. Like I was just saying, the different resolutions even within V1.
Yeah, I think that's going to be the
Yeah.
first principle.
There's also
And
just
then
go ahead.
sorry.
I was
Oh
going to
yeah,
say,
yeah.
All right, as host, Jeff goes first. All right,
All
here we
right.
go.
You know what this reminds me? It reminds me of CDMA, which is the technology they use in cell phones, how they just, when you basically have, if you don't know CDMA, it's funny. But if you don't know what CDMA is, it's collision detect. So you have an algorithm, but when two things communicate, like collision, you have an algorithm to figure out how much to wait before you try again. Niels and I were doing that just dynamically right there. The it's an interesting biology question. We think of of course there's cones and rods in the retina, and the rods are black and white, and the cones are color. And the rods work in dim light, and the cones don't, and things like that. And in general, the general rule is that the cones are sort of focused in the fovea, the center of the reps, and then the rods are on the periphery. But there's rods throughout the whole retina. So even in the fovea, there's cones plus rods, where in the periphery it's mostly just rods. And I'm wondering if somehow I'm wondering if the rods and the cones have inherently different if they're processed in some sense that the outputs of the retina, the magnocellular cells and the parvocellular cells, which are partly associated with rods and cones, if even within the fovea, are there columns that are getting larger and smaller rod areas and larger color areas? You know what I'm saying? It's like this idea that there's a uniform um, receptive field size. All the learning modules have the same receptive field size. Earlier I said that's not true in the periphery of V1. I wonder if it's true within the fovea itself. If
Yeah, I
there's
mean, yeah,
some
when you look at
right,
like a lot of those old papers, it seems like it's not true even within like a narrow region, because like you have some columns that have quite wide inputs and some like there's quite a mix of the receptive field sizes
right.
right. Within a
The more I'm thinking about it, you could take a single region. I'm trying to say, and what's if I had a whole bunch of learning modules and I intermixed them, where some had large resolution or were narrow focus and some were widely focused. They're all learning the same. They're all learning the same model. They're all learning the same model of the word, or the same model of the logo, or the same model of things, because all of them are learning the same thing at once. Um, and so they would build. It might work just fine. In fact, it might be a way of handling this sort of resolution issue without requiring V1 and V2 to have different magnifications. You might be able to all fold them into a single region like V1. So V1 has a lot more capabilities than for dealing with scale than we thought of otherwise. I don't know if you're following all that, but I'll shut up in
Yeah.
case.
I mean,
So
that also kind
basically,
of,
like instead of having a narrow range of possible receptive field sizes in V1, you're talking about like if we just artificially had quite a wide range of receptive field sizes, we could
Right.
kind of
Well, we know
manage
we
it in
know
one
that's
one
we
tier.
we know that's true in the periphery of V1. That's
Right.
absolutely
yeah.
true. That's a fact. And so the question is, could there be some of that extent in the fovea as well? And yes, that's the question. And in which case, they're all learning the same models, but at any point in time, some of those models will be more important than others. But they all
But
learn the
they
same
would
models.
be learning different models of the same object, right?
Right,
Because
right. Well, that's what I meant. I'm saying that's what I meant. Yes,
Mhm.
They're all learning models of the same object. Every column learns its own set of models. There is no. Everybody learns its own models. At least every column of the cortex learns its own models.
Yeah.
But they would be doing. They would be learning. They always learn the same object at once. And so we'd be learning at different resolutions even within V1.
yeah,
I'm just
like
thinking.
Yeah.
maybe just I'm just sharing a
Yeah, that one.
paper.
Yeah,
Right.
I
I
love
show this
that.
one a lot, but
Yes,
but it
right.
is useful. But it's just you have eccentricity here on the x-axis, sort of, and then these are the different layers. and then the size of these squares. This is moving edges, but it represents the size, how big the edge was. And I guess the general point is that maybe there's a trend, and certainly more comprehensive studies, they've found a trend that as you go more towards the periphery, the receptive field
Yeah,
increases.
this
But you can
is
see it's quite a mixed bag.
right. But
And
I
so
think the thing I was talking about, I think it's quite dramatic. So I'm surprised it doesn't show up here. If you go like the eccentricity is how far away from the center of the retina, right? So this goes out 20
I think
degrees.
here you see it maybe a bit better. Like, I mean, these are absolutely tiny,
Right.
whereas these are obviously quite big.
You said it
So
yourself. Remember, you
here
used to
it's
say,
more
Neil,
clear.
the phobia is like your thumb at the width of your thumb at
Yeah, your fingernail held at arm's length
well, how many degrees is that?
is that's 1 degree.
So if the phobia is 1 degree, then almost none of this image is really showing the phobia. Maybe only the that little one right at the 2-3 boundary you just talked about.
Right. Yeah, like this one.
Because all these others outside of phobia. It's interesting.
Yeah. And that also, I know that's at least in humans, because it gets complicated. Because I mean, obviously, other primates are generally foveal, but some animals don't even have a proper phobia, or they have like a
Right.
horizontal
Well,
phobia because all they care about is predators running
right.
towards them.
So
Okay.
I guess
That
another
was
thing that I'm thinking about is like we're modeling the simplest kind of receptive field that's in V1, but they're not all very basic V1 simple cell edges. Like in principle, there's all kinds of receptive field shapes that we ought to be able to plug into a 2D sensor module or have another sort of richer uh, variety of receptive fields that we could plug in, but we'd
mean
just have to
like
implement them differently.
like beyond orientations.
Yeah, like corners. You know,
Yeah.
there's end stop cells and there's, you know.
Well, end stop cells are consistent with this. Um, well,
Yeah,
But
you
by having a
know,
sort of a slightly richer repertoire of potential features that are still two-dimensional, but they would give us a bit more,
right.
you know, we can
Well,
stack
this
them on top of this as well.
right. So, I mean, this is what like Bruno Alshausen, shown you can take a patch and turn it into sort of its principal components, and
Mhm.
and then you can recreate images, and some of those principal components, a lot of them look like edges, and some of them look like other stuff.
Right.
Um, and that would be what the spatial pooler does too. The neural algorithm, the spatial pooler that we've came up with, that does the same thing. So you can do that. The problem with that is very quickly the number of components that it mushrooms extremely large. Like you can think of we have to take these orientations and we have to be able to rotate them, right? Because that's part of the whole algorithm we have. So you have to be able to rotate these. And you're going to represent these in the brain, you're going to represent them in mini columns. And if you start coming up with more components like, oh, checkerboards and edges and corners, all of a sudden you can end up thousands and thousands of components that would be difficult to represent in many columns that wouldn't occur very often.
Mhm.
So that's something that maybe Monty could do beyond brains, because Monty doesn't have the same restrictions as brains. So I guess, Scott, I'm saying you're right. You could represent more sophisticated features, but it can get explosively large very quickly
Mhm.
if you're not careful.
Yeah, and in terms of how this is implemented, I guess there's a few approaches we could have taken. One would be, kind of a more learning one, like you say, with something like the spatial pooler. One was kind of like having a fixed bank of filters, like the Bohr filters, and just
Hmm.
saying, reading out from those. The one we ended up going with was most similar to what we do for surface normals right now, which is essentially like a mathematical algorithm that to kind of describe it succinctly, looks for the strongest gradient and the orientation of that gradient, and then outputs the edge. So in some sense,
Hmm.
it's kind of the most interpretable. So it was kind of in keeping with that theme of what we've been kind of doing with Monty of having kind of a clearly kind of engineered solution, but that also maybe makes it less flexible. So you could imagine in the future that you could have
Well,
alternative ways essentially of extracting
you you could
these
easily
morphological
replace that,
edges.
right? I mean, I assume you could
Right.
just unplug one and plug another one in, right?
Exactly. And you could even
Uh,
have different different learning modules that have different sensor modules that have different
Right.
approaches.
Well, we already have that in some sense. We have the 3D point normal model. Now we're adding a 2D one.
Yeah.
Yeah, I think that's right. I mean, I guess this is a great start. We're off and running. It's working. But we wouldn't be surprised if we can come up with better versions of this and alternate versions and more sophisticated versions and ones that learn and ones that deal with different type of environments. You know, if you're looking at LiDAR or something like that, you might end up with a different methods for doing something similar.
Oh yeah,
Yeah, and
definitely.
that's something I feel like would be really nice in the longer term is finding a way that we can take the principles of kind of center surround and just no matter what the modality is, as long as there's kind of change out there, that it would find essentially
Right,
kind of the equivalent of morphological features in that modality, whether that's the
right,
frequency in audio or patches on skin
right,
on a tactile robot. But
right.
but we don't have that kind of implemented yet. But
Well, it seems like the brain is, as you just said, the brain basically relies, as far as we know, relies on one method. It says, give me center surround receptive fields, and I'll run them through a learning algorithm. And I'll pick out what I can. But that we don't have to stick with that long term. We can come up with all kinds of better stuff. So, but anyway, we just got to get going. So this is the start, which is great.
I'm just
Scott.
recognizing that the color of the logo actually doesn't really matter, right? Like this is immediately going to, sorry, color of the lettering, for example. So if this had been a solid red, so it's
That's
basically
yeah.
invariant too, right? Am I correct?
Yes.
So
Um,
that leads me to, I guess, two questions or two things. One is that's really cool that it's invariant to color, but secondly, how would we be able to go, oh, that's a blue lettering of the logo versus, oh, that's red lettering of the logo?
okay, so the reason why it's invariant is because we're you know, we the first step of the algorithm, or one of the earliest step, is we're converting the RGB to
Mm-hmm.
grayscale. So that's why it just depends on the intensity change in grayscale. Doesn't matter what the actual color is. Um, Vivian has actually suggested maybe we could just look at a gradient in the R channel or the G channel or the B channel. That is one
Mm-hmm.
way to kind of see, like, okay, if I want to just pick out edges based on changes in one channel, um, again, I just didn't do that because it's a little like, at least in the beginning, it was like the use case was a little bit limited. I think the other kind of idea that I had that was maybe better than RGB and turning to grayscale was, taking the HSV and just looking at the changes in hue and keeping the S and the V saturation, and I forget what the V is again. But yeah, but that would be like a way to say,
I, I,
okay,
I'm I'm sorry. Are we talking about how would we recognize blue versus red, or are we talking about how is it invariant to blue? I mean, are we saying how we got rid of the color, or are you saying how you would incorporate the color? I'm confused.
I think Scott was asking. So yeah, I think it makes sense in general to look at intensity, certainly for as the basic one, and like we're doing here. But yeah, this is just extracting the morphological feature, which is the edge. We also have the feature which is hue, or it could be just as well RGB. And so if someone is learning a model of the letters, they're going to be getting the edges for the letters, but they're also going to be getting color like blue, just like we do with the mug, that we get the surface normals and we get the color of the mug. And just like we do in that case, the model is at its core, it cares about the morphological features and their orientation. Secondary is any other kind of any other non-morphological features that may have been learned, like color. But one of the nice things of this is maybe this can move us towards having these compositional models where the texture of ceramic, like red ceramic, is itself a surface model that you might be recognizing um, and applying to a 3D shape.
yeah.
Does
I
that
guess
answer your question, Scott?
I think so. Is that? But let's say we want to say it's a red versus blue lettering. At like
yeah.
at which level do we need the second tier
I mean,
basically?
it's the same question. I think whether it's a red mug or a blue mug, we haven't totally
Okay,
agreed on how we would
right.
communicate that.
Okay.
Yeah, further up the system.
I posted a link to a paper last week about the V1 and V2 organization, where I was talking about the size of the columns and the hypercolumns.
Oh
And
yeah.
that paper was really, really interesting and eye-opening for me. And it was talking about how color is represented in both V1 and V2. And it's basically saying, okay, these mini columns are arranged such that you're overlaying multiple dimensions on top of one another. One of the dimensions is orientation. Another dimension would be ocular dominance, which you could think of it as depth, and another dimension would be color. And so mini columns, there'd be some mini columns that respond to all combinations of these things. So if a mini, so it would be like it's a clue to the answer here. It seems like even if you arrange the if you sort of imitated what we're seeing in V1 and V2, where these sort of hypercolumns were millimeter square, and they have these mixed representations, and you assume that all these columns are being used, that you could learn models that are independent of color, but you can learn models that are specific to color. It suggests that there's a general answer to this question about how do you incorporate color and non-color in the same models. I'll just leave it at that. It was like, okay, that's the way to go. There's big clues in that paper, and so I think just you could have models that are tuned to color, but also respond to at the same time if there's no color. The same column could do both.
Mm.
Mixing up if you follow the mini column approach, where some mini columns respond to these things, and so if it's always blue, then only the blue mini columns would ever get to learn the model. But if there's multiple colors, then other ones would learn it as well.
Mm.
Anyway, that's a clue to the answer of color.
Yeah. I had one more thought about color, which is that when we look at a mug, and we always look at it under a certain lighting condition. So I have this kind of black, okay, it's kind of black and gray. If wherever the light is hitting directly, the camera is picking up, more light gray or, almost white, while, where there's kind of the shadow, it's more black. But our brain doesn't think that this is like all different colored. We are perceiving as like this is the top is a black mug. It's just that the lighting changes the, absolute RGB values that we're seeing.
Yeah.
So so I was thinking that instead of, just when we're perceiving color, it actually kind of important to know the geometry of the color so we can actually adjust. Oh, like, I'm seeing white, but because it's, at the close to lighting, this color should be actually adjusted back to black so that we can kind of consistently
Well, this
represent.
is like remember the gold blue dress
Yeah, yeah,
meme,
yeah,
right? It's
yeah,
the exact same image, and some people saw the dress as gold, some saw it blue. They were swear it was so clear to them, and yet
yeah,
and then but the answer that that I heard that most people had settled on was that you were making different assumptions about the direction of the light, and so
right,
on the people
yeah,
who saw blue, they weren't thinking where's the light, but their brain had interpreted as if the light was coming from one direction, just like you were talking about.
yeah,
I don't think we've ever. I can't remember any of our research meetings where we talked about this issue about, the perception of a color is really not, it's the perception of the color. It's not the actual color, right? And
yeah.
the whole problems of percepts. So we've never really dealt with that.
Yeah, maybe this should be one of the topics, honestly, because I mean that was
Uh,
actually, well, we'll see.
yeah, it's a really
Like,
hard problem. Well, I shouldn't say it's a really hard problem. I have
Yeah,
not made any progress thinking about it, so it might be an easy problem, but I just haven't been able to make progress on it. Um, I always felt like the problem of this sort of our perceptions, because the colors don't really exist, right? The blueness and redness don't really exist in the world; they're just frequencies, and there are different cells responding. So by the time it gets to the brain, there's no blue or red, and yet we somehow have this perception of these colors. We've never really talked about that here in this group.
yeah.
I don't think we
At
have.
at least algorithmically, I mean, so the reason why I said this is because um, so one of the issue that I ran into is that because this algorithm is based on gradients and how color like intensity is changing across the patch, I noticed that when we're looking at a really curved surface where because of the illumination, it looks darker on one side than the other, it would actually pick up, that as an edge when it's really not an edge. It's just color change because of the different illumination.
But wouldn't it have to be a
Um,
very, very sharp curve to make that happen in a
yeah,
small
it
patch like
does.
this? Right, because this
Yes,
is a very
yes,
small patch, so the gradient over the small patch would be pretty minimal. And
yes.
to have a really strong gradient over the small patch, you'd have to be a very sharp radius, and that would be an edge.
Yeah. Well, yeah. Yeah.
No,
So I
wouldn't that
mean,
be?
yeah, that's true. And we can just adjust that by, like just changing the angle that we're looking at an object, so there's not a sharp edge. But I mean, it's just cases where like I'm looking at like the edge of the. I mean, so it's a very rare case, but all I'm saying is that the way that we're extracting color is just literally reading off the RGB. But I mean, at least algorithmically, there's a way so that we can correct for the illumination. That's all.
All right. A bigger problem that's really surfaces right away in real world images is shadows, because
Yeah.
shadows make huge edges, and in
Yes.
perceptually, we don't even notice them. They're not. We
Or
just
Yeah.
did.
yeah, or that's the weird thing. Like it's one of those things where we kind of notice the absence or when they're wrong, but we're not good at kind of understanding them. Like if someone was to tell you, "Oh, draw what the shadow should look like" or something, you
Right,
you would
right,
struggle
but
to do that. But if someone showed you a photo with no shadows in it, it would immediately look flat and weird.
I don't know. I don't know. I, I, I might want to challenge you on that one, Niels. I like to see that one. Um,
Really? Okay. I mean,
Yeah, on
yeah,
not
that,
This is
not so
something
I
strange,
mean,
I
not like crazy weird, but like just for
I'm
example, in
looking
like
at. I'm looking.
video games, it was a big innovation when they were able to add shadows that made it look much more realistic.
What makes it more realistic? But the question is, I'm looking at my picnic table outside my window right now, and it's lit up in the sun, and there's a big shadow underneath it. Now, if I didn't have that shadow underneath it, I don't think I'd look out my window and go, "Wow, what's wrong?" Maybe it would take me a second, but if I flash that image in front of my face, I would say, "Oh, there's a picnic table." I wouldn't say, "Well, I don't get that picture. I don't know what it is." But in reality, looking out my window, the strongest edges everywhere are the shadow edges.
yeah,
They're like it's like
Niels, did you see the video that Scott shared in Coffee Corner of the Wrecking Ball with the dog?
No, I don't think so.
Oh,
What is it?
was that recent?
Because yeah, I definitely didn't think about the shadow at all until you pointed it out, Scott.
Is
you
And
want
that
me to
is
share
that
it?
post was that post? Yeah, please
sure,
share it. That
yeah,
would
if
be.
yeah,
you're
yeah.
Sure.
okay with sharing it.
Um,
Well, now
Are you seeing the dog?
I see the
Yeah,
dog
yeah,
and I see the
Yeah.
we
wrecking
see
ball.
your screen.
Do you see the wrecking ball?
Yeah,
Okay.
Yeah.
there's no shadow
right.
on the wrecking ball, but definitely got a shadow.
So now,
Yes,
unfortunately,
it looks very flat. It
I
looks
was
like an old
biased.
school video
I
game.
I knew we were talking about. I knew, yeah, it doesn't look realistic. I knew we were talking about shadows. So if I so I had a prior. If I didn't, what would I have thought if I didn't? Would I've noticed the shadow was missing?
So
I
that's
Um,
what
think
I was
so.
saying. When I just watched the video, I didn't notice it until Scott
right.
commented on
But you noticed something was off, I'm guessing. Like it
Well,
didn't
it
look
doesn't.
real to you.
It doesn't look real, but I don't think it's because
It
of the
looks like it's
shadow.
superimposed. It looks like it's superimposed kind of
It is it
To
is it
to
was it
me, the
really
Partially,
chain
filmed,
looks
the
or
real.
was
lighting
it was
highlights
it
on it is
or
off
was
too.
it really was this a CGI thing, or was this really a ball that the dog avoided?
That's a CGI.
Because
CGI.
that the reason it looks fake to me is not because it doesn't have a shadow, it's because it's got that CGI-ness to it. Like the edges of the ball are too sharp,
Right.
or the shadow's not. I mean, the lighting on the ball doesn't look right. And the chain's wiggling incorrectly. I mean, a whole bunch of stuff here.
Yeah.
Um, so,
But
for
I think the
example,
I
lighting on
mean,
the
I think a
chain is
you
ball
quite
doesn't.
good.
definitely
no, look,
stuff definitely looks off if it doesn't have shadows.
that if that was a real heavy ball, that chain would not be flexing at all. You see when it swings, you'll see that it bends in the middle.
Uh,
It's like right. It's like
Yeah.
like right there. It's like it wouldn't do that. It wouldn't do that. If the ball's that heavy, that's it. That's
Yeah,
incorrect. It wouldn't do that. The chain would be. That's what struck me. The chain
interesting.
would be taut the whole time.
So that's
There's no.
material knowledge. That's physics
There's no way
knowledge.
the ball's gonna. There's no way the ball's gonna go up in the air enough somehow to get the chain loose. I mean, it's not gonna happen. Just that's what.
Yeah.
Uh,
So that struck me as odd. All right, I think this is an
uh,
example that you actually wouldn't necessarily notice that the shadow is missing. And there's other things about the whole image which screw you, and it's CGI. Um,
Yeah.
well, I thought it
but
looked
look,
realistic.
but
So
look at the
anyway,
shadow
we're
under the dog. The shadow under the dog is very sharp. Those are like the sharpest edges you're seeing in that right around the dog there.
Yeah.
And yet we totally discount them as part of recognizing the dog.
Yeah, I think
It's
that's
just like,
interesting. Yeah, that we don't really see that as like in an object in the same way.
right. I know this tripped up a lot of early computer vision programs. And it might trip up an algorithm you just did too. I don't know.
yeah. I mean,
Well,
I
apparently
never
there's a
considered.
way to render there's shadows and stuff in Blender, but I haven't figured it out. It's complicated. There's a whole extra pass to figure out how to get shadows to project onto stuff, but I haven't figured it out.
Well, we're looking at the logo on the coffee cup. There's no shadows there, so
Right.
Yeah.
um,
So I
um,
think though, in terms of this whole like discounting of the illuminance, that's like jargon. It's like it's going to require some global. It's not something we can do at a single patch only level, and like adjusting for the color, knowing what the illumination is, the overall illumination is something that there's a more global mechanism for pooling across the spatial field to help the patch.
maybe.
I think the shadow is a really good problem. I mean, so we did think a lot about making sure we eliminate edge between the object and the black void that Monty lives in, because that's not a real edge, but in an image, it will look like an edge because it's against a black background. But the shadow, it still wouldn't catch the shadow because there's no depth is continuing. I guess okay, so that's actually a limitation of the simulated world that Monty lives in. It's like everything lives kind of, or objects are just floating in this black void space, and it's not sitting on any surface, so we never see any shadows. But we'll
Well, I mean, the
definitely.
question is shadows just something that we learn to not pay attention to,
I
or
don't
is
know.
it some? Is there some?
It's
I would
interesting.
think it.
They're not stable is one thing. It's
Well,
like
no, neither
they,
is the dog, right? The dog's running, and imagine. I just was imagining the picture of the
it's
dog
true.
running there, and took the picture. Imagine that the wrecking ball. I imagine the video, but the dog wasn't in it, but his shadow was. But just forget about the wrecking ball. I was just imagining that shadow moving across the ground. I would definitely notice that. I would say, "What the hell's that? What is that thing moving across the ground?" It
Yeah.
looks like. But when I see the dog, uh, I don't see the shadow at all. So it's like maybe
Yeah,
this
that's
is
what makes me feel
attention
like,
window.
yeah, we are modeling it and predicting something there, but
It could be that
imperfectly. But
it
I
might
think we
be
do
that
have some coarse level of at which we model and expect shadows, basically.
I don't
I
know.
think
It
so.
could be. It could be I'm attending to the dog, and when the dog's moving, and if I have a model-based attention window there on the dog, and basically as I'm attending to the dog, the things that aren't the dog aren't paying much attention to.
But again, it's
And
weird. Like you'd think something that's really dark that's also moving fast would grab your attention. And
Yeah.
unless you, in a model-based way, are kind of explaining it away. But it does feel like the only way you could have a model-based representation is at a higher level. It's not going to be like shadow modeling. I don't think it's going to be specific to dogs. It would be a more generic thing where it's like, okay, objects with this approximate shape, I'm going
I
to
guess
expect this
see,
approximate kind of
see,
shadow.
I would argue. I'm going to argue against that. I'm going to say that if that shadow was incorrect for the dog, like for some reason I don't know. I bet you I wouldn't notice it. It's
That's
almost like
why, yeah, that's what I'm saying at a course level. At a
I'm just
course
saying
level.
it's more like I'm attending to the dog, and therefore I pay no attention to the thing that's not the dog. Um, It's anyway. I don't think we can solve
But it's
this
because the
problem
shadow's
today.
moving with the dog. Like imagine now the
Right,
shadow's doing something totally different. Like it starts moving in a different direction, or
right, right.
I feel like if it was sufficiently weird, then
If
you
it
would
was
definitely
sufficiently
be like,
weird,
what the heck is
absolutely,
going on?
absolutely, totally, I agree with that. Um,
Did you
interesting.
pay attention? Did you see the cat?
I did, or
What?
this time I noticed.
The cat? Oh, in
Yes.
the
Yeah.
picture. Yeah, I did see the
Yeah, yeah.
cat. It was on
I
the
didn't
left
notice the
side.
first time. Yeah, very cute, just rolling around. Okay, I'm getting distracted now. Okay, so I'm gonna go back to the slides, even though I have like thoughts on shadows again, whatnot. Um,
Can I just
uh,
point out one other cool thing? I mean, like, so
oh yeah, yeah, yeah.
this is from shoot, wait, if I can find it. This is from the museum. Sharing again.
Twist Museum.
Yeah, I mean, Twist Museum is the museum that keeps on giving. I mean, this is another
Yep.
example of the luminance discounting problem. I don't know if you guys remember this, but there's like a yellow light. These are all color umbrella. Oop.
Oh,
These are all color umbrella, and because of the light source, you might be fooled into thinking that this is all like, this is the blues, reds, whatever. And so there's this like global, and
Yeah,
maybe it's
this
not the
was a
best
really
example of
strong
this, but
one.
Well,
I
yeah,
was
yeah.
gonna
yeah,
say,
personally, I
Which,
perceive it as black and white generally, right? Does anyone
yeah,
see color?
but it was really extreme in the like when they would change the light to white. Those umbrellas were really colorful. Like all of the colors are in there.
yeah,
And then they changed the light to yellow. And yeah.
But
so
yeah.
what is it? What is
it's a single wavelength light, so you cannot like there is no other color information in this.
Yeah,
what's
maybe
the
this
what?
isn't the best example.
So I mean, to me, this is just looking like a black and white picture, right?
But the
Um,
umbrellas
Yeah.
are actually has real color spanning the
no, no,
rainbow.
of course, no, of
Yeah,
course. But if I'm watching a black and white movie, all the people and all the things in it had real color, but they're-
Yeah.
yeah,
you're just taking it. It's the same effect. You end up with a mono,
Yeah, which
Yeah. A
is
better
maybe just to
example would be
comment
more
on like
like the showing
go
the
ahead.
scene under two lighting conditions, and you do discount them pretty easily.
Yeah,
It's
like
crazy.
the
Yeah.
dress. But
Right.
yeah, one thing is like yeah, we use hue right now in an effort to like kind of move away or like yeah have some kind of invariance to illumination, but it's not a perfect solution because as you bump up the saturation, like if something's very bright or very dark, hue is inherently noisy because like there's always going to be a hue value, but what's the hue of true black, whatever.
hmm
It's as far as I'm aware, Monty's or Habitat is basically just going to come up with a number,
hmm
and so that has its own problems, but
yeah.
yeah.
we're getting
Um,
pretty far afield here.
okay.
Um,
I
I
only have
like.
like a couple of slides left, so maybe I'll go through that. Or what are you going to say, Jeff?
I was hoping we can still get to Vivian's part today.
Okay,
So,
yes, okay. Sounds good. Yeah, well, I'm only a couple of slides. Completely switching topics. Just to touch briefly on how the 2D reference frame was learned. Okay, so forget about edges. We're done with that discussion for now. The 2D reference frame. So this is an interesting reference frame in the sense that it's a moving reference frame. It moves along the surface of the object that we're observing. So when we first look at an object at a certain point, like this black point here, we can construct a tangent tangent plane based on the surface
Maybe
normal
to
that we're.
anticipate some possible confusion, the reference frame you're talking about right now is not the reference frame that's being learned. Like, as in,
Uh,
there's a single 2D reference frame that's going to be
yes,
learned. This is a
yes,
reference frame that is a technique in order to extract and correct
yes,
uh,
yes.
edges.
Yeah, 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 yeah. I mean, it's very hard to like draw. Like I don't have good like animation skills, but you have to imagine that like if you move, from here to here, your your tangent frame has rotated, but the way that we accumulate path in 2D is that we have to kind of unroll um unroll it out and kind of continue on the original
are you
substantial.
just showing how do you learn a 2D object when it's presented on a 3D surface? Is that
Yeah,
what this is
yeah,
about? Okay, okay,
yeah,
great.
yeah.
All right.
So I mean, this is the best animation that I could come up with. So I'm sure if you were not me, you could have done better. But I think you get the idea. It was just very hard to explain this in code. I remember like what's happening all here. Anyways, the probably the relevant practical question is like what kind of surfaces can be unrolled. Again, this is more of note to the user, but basically, so if you have like things like plane or cylinder, obviously you can unroll it just fine. Like as in unroll without distortion, just fine. If you have sphere, obviously you can't. I mean, you have seen maps of Earth. I mean, there's huge distortions there, depending on how you create that map. And of course, like most of the objects that we deal in real life cannot be unrolled as a whole. The point that I want to make is that if we're not trying to unroll the entire object. We're only trying to learn, or like for now, we're only kind of unrolling parts of it. And as long as that part is somewhat like a plane or a cylinder, like a mug is a cylinder with a handle, and if the logo is on the mug, if logo is on the cylindrical part of the mug, then actually we can learn a pretty good representation of the logo, even though the mug as a whole cannot be flattened into 2D. So basically like, okay, yes, we have a lot of odd shaped objects, but probably don't worry, as long as it's locally unrollable, it's fine. And then on the flip side, the caveat is if you do unroll something called non-developable surfaces like a sphere, something that cannot be flattened, then the learned model will depend on the path you take to learn the model. And this is kind of a thorny issue because obviously during learning or inference, we might take different paths and that might actually end up with two different models, even though we have two different 2D models, even though we have the same 3D object. So in that case, the 2D representation is not that useful.
Yeah,
Well,
but
I
I guess
think
the
it's
level of distortion isn't that much as we kind of saw with the inference results before. And you can imagine, like, we're not going to learn just from a single example. So the
yes.
kind of model we learn from multiple exposures is probably good enough. I mean,
Yeah.
in the same way that like an approximate
and
2D map
I
of Earth is good enough to look at a globe and vice versa.
yeah.
Yeah. So just caveat there. And obviously the amount of distortion really matters on like how much your principal curvature
I
value
don't think we're
is.
good at this at all. So I mean, in terms
Yeah.
of like if there was a logo on a Raptor on a ball and the logo was very large relative to the ball, it just wouldn't work. And I don't know what it'd be hard to learn it. It'd
Yep.
be very
Yep.
confusing.
Yeah.
Okay.
So yep, that's it. Here's, I guess, the summary. So as of version 0.33, we have a new capability to learn surface models and also do inference. This is enabled by two kind of independent but related functions. One about detecting dominant edge or detecting dominant orientation. The other one learning a 2D tangent frame. This is, I mean, it's a step toward many things, but the immediate goal of trying to recognize compositional objects. And now that I have done this presentation, there will be like a documentation updated in our README. And I have a little sneak peek, but so you will see this soon, whoever gets to review this PR. And yeah, so thanks everybody who helped out in the project. I think basically everybody, minus Benji, was involved. Benji, I was excited for you to join, so I guess you were motivational help, motivational support. But yeah, basically everybody, you might think that you didn't work on the 2DSM, but you probably did. So Vivian Mills obviously helped with the entire research phase, the entire 4 or 5 months I took to get here. Scott, you made a compositional data set, which was very useful. Rami is our first user, and he's already creating new PRs and actually applying this to more interesting problems than just me making sure that it works in principle. Jeremy and Dale had to pair program with me for about a month straight, so that's already a feat. I'm sure I was a joy to work with. And Tristan, we didn't get to work like directly, but the initial kind of directions that he set for kind of testing and also like thinking about the overall architecture of how we should kind of shape features. At least that helped me with my thinking process. And I didn't emphasize this in this research project here, but we have also made a lot of effort to make so that the next feature, that user wants to add, or the next reference frame, like these are kind of clearly standardized so that the next progress will come faster. So always kind of nice so that the next iteration project like this will go faster.